Welcome back to chapter 25. We're now on to video 3 where we discuss the index of refraction. So this is section 5 in the notes. You will see that the index of refraction is defined as the ratio between the speed of light in the vacuum and the speed of light in a particular medium. We symbolize the index of refraction with a lowercase n, and the speed of light in a vacuum is symbolized by the letter lowercase c, and the speed of light in any kind of a medium would be just a little v. We're going to use this equation, n is equal to c divided by v, in a few examples. So you'll want to know the formula for your study guide. What it does is that as light travels from one material into another, the speed of light will change. And this changing in the speed of light actually changes some of the other optical properties that we see. Things with a high index of refraction slow down light noticeably differently than things with a low index of refraction. So we are down now to looking at this refraction or bending of light and Snell's law. We're going to look at the bending of light and Snell's law. So light bends or refracts as it passes from one medium into another. The index of refraction, like I said, is the ratio of the speed of light in a vacuum to the speed in the medium. So n is equal to c divided by v. The index of refraction, because both c and v are measured in units for velocity, n has no units. It is just a number. Some examples of indices of refraction. So in air, the index of refraction is 1.0003. In water, it's 1.3333. In certain kinds of plastics, it's in the neighborhood of 1.5. In certain kinds of glass, it's in the neighborhood of 1.5. In a diamond, it's over 2. So you can see there's quite a range of values. Every transparent material has its own index of refraction. Now, one of the things about Snell's law, we can rewrite it in terms of the angle that the light gets bent as it travels as through the material. And this is a form we're going to use quite a bit. So you'll need to know this, that n1 sine theta 1 is equal to n2 sine theta 2. You need to know this number, this formula. You need to know that the index of refraction in medium 1 times the sine of the angle that the light makes in medium 1 is equal to the index of refraction in medium 2 times the sine of the angle that the light makes in medium 2. A large index of refraction tells you that you're traveling at a slower velocity, and that means the light can be bent or refracted more closely to the normal. Remember that the normal is an imaginary line that makes a 90-degree angle with the surface. What's really cool about this is that the bending or refracting of light gives us all kinds of optical illusions. So if you are standing in a pool of water and you look down at your feet, you will notice that your legs look really short. Or you maybe have noticed if you put a straw in a glass of water, it looks bent. Those are both optical illusions created by refracted or bent light. Your mind can't account for that, and so it traces the light back in a straight line, which the light didn't follow, and gives you incorrect information. Let's look at a couple of drawings to see if we can make some sense out of this. So this first one is meant to be the straw in the glass of water. You're out here looking at your glass of water. Here's our straw. Light from the bottom of the straw comes and it hits the surface. This tall vertical line that's dashed is our normal to the surface. So the liquid will be more dense than the air and have a greater index of refraction. So when light goes from high index of refraction to low, it bends away from the normal. So I know it's going to come in and bend away from the normal. When your mind sees it, it traces it back in a straight line, and your mind's going to infer that the bottom of the straw is up here. This is the same would be true if you were looking down at your own feet. If instead of a straw, we thought of it as your leg, you would see your leg is much shorter. Another mirage that's possible is a desert mirage. I overshot again. So desert mirages are a result of the temperature gradient of the air. The air over the sand in the desert is the hottest, and as you get higher and higher, it's going to be cooler. And it's this temperature gradation that gives us the mirage. It's this variable change in the temperature. So if we look at, well, I do it every time. I guess it's because my image is a little large. Let's see if we can zoom out, and then I can get it all on the screen at one time. That might be possible. Or there we are. All right, so we've got the sun up here, and the sunlight hits the palm tree, and some of it bounces off and goes straight to your eye and you see it. Some of it hits the palm tree and it comes down, but because the air over the ground is less dense than the higher air, it causes this beam of light to bend, and it actually makes a curving arc. And so when it gets to your eye, you see this beam, and your mind traces it back in a straight line and says, aha, we've got the top of the palm tree down here, but your mind sees the top of the palm tree up here because of this other beam. And now it has conflicting information. You can't have a palm tree with two tops, you know this. So your mind makes the inference that the only way possible for an object to have a top and a top is if there's a pool of water and you're looking at a reflection. So your mind assumes there's a pool of water down here and that you're looking at the reflection of the top of the palm tree in the pool of water. You actually have seen this kind of mirage on the highway. Very few people have seen it out in the desert, but a lot of us have seen it on the highway. You probably have been driving along and noticed those puzzles on the highway that disappear when you get really close to them. So what you're really seeing is a mirage. You're seeing a double image of something in front of you. It could be an automobile in front of you on the road. It could be a tree limb. It could be a lot of things. The highway is like the sand in the desert. The air over the highway is the hottest, and as you go up higher, the air cools off. So you have a temperature gradient, and what that does is make the light over the road arc, just like it did in the little cartoon drawing of the desert mirage. And you end up seeing two images, and your mind says, aha, the only way to correct for this is if there's a little puddle there. When you get closer, and let's back up to this previous example. When you're standing right here, you can see both images. But if we take our little man and we put him right here where my crosshairs are located, well, I take that back. Let's put him right here. You would see one of the arrows, but you would not see the other because you're physically in the wrong place. You have to be in just the right location to get both pieces of information. So when you move closer or farther away, the image is going to, the mirage will disappear and you'll only see the object itself. You won't see the imagined reflected image. And the same is true on the highway. On the highway, the image disappears when you get to be the wrong height. So if we look out, this is a photograph of a car on a hot road, and you can see these little shiny places. They're those little puddles that I talked about. What you're really seeing is a double image. And on this one, you can see the car where my crosshairs are. But here in the little mirage puddle, you're actually seeing, your mind is making you think there's an image there and that there must be a puddle of water. And again, as you get closer, you're at the wrong height and the mirage disappears. Let's talk about total internal reflection. This is what fiber optics is based on. So with fiber optics, we have light moving from one medium into another. It would undergo both reflection and refraction at the interface, at the place where the two mediums meet each other. So if we start out in this top material, the light ray comes, hits the surface and bounces off. That's the reflected ray. But if both materials are transparent, the light would come from the top surface, and at least some of it would travel through into the second, which in this case I'm calling water, and you would get a refracted ray. So when light goes from a medium with a high index of refraction into one with a lower index of refraction, when it goes from high to low, you see total internal reflection. We get total internal reflection when that happens. And this is a photograph of a laser shining light into a container that has a high index of refraction. So the light comes in, you can see the beam come up and hit the surface and bounce down, and then come up and bounce down and come up and bounce down. This zigzag pattern is called total internal reflection. So at the interface, some of the light reflects down, but some of it travels along the interface. You can see how this little top edge looks very bright. That's the refracted ray. The one that comes down is the reflected. The one that travels along the interface is the refracted ray. And when you're at just the right angle, instead of having some of the light leave the medium, it stays trapped. So part of it just reflects up and down, and part of it, the part that would normally escape, travels along the interface and sort of makes a little edge of it glow. This is called total internal reflection. And in this, the angle of reflection is 90 degrees. That leads us to something called the critical angle. Remember, I said you can only see this when the light's entering at just the right angle. Well, just the right angle is the critical angle. So we need something so that our angle that we enter at gives us a refracted angle of 90 degrees. And the sine of 90 degrees is 1. So the formula for the critical angle is that the sine of the critical angle is N2 over N1, where the two N's are the indices of refraction. N1 is the material you start out in, N2 is the material that surrounds it. So light starts out in material 1, and material 2 is has a lower index of refraction. So big number going into little number gives you a number less than 1. Sine has to be 1 or less. If you get an error with this equation, it means you've switched the two indices of refraction. You'll see this in the examples that we do. We'll do some numeric examples in class. So we see uses for total internal reflection in medicine and in communications. If you've ever had anybody, you've injured a knee or a shoulder, they might make several incisions, and in one they would insert a light source, and another they would insert a fiber optic camera in order to look around, and the doctor would look at the image then on a video screen. This is using fiber optics, and it requires that the light stay in the fiber in order to enter into this little cavity that you put it in. Another place we use it is in communications. When you have signals travel over fiber optic cable instead of over copper wires. So telephone signals used to travel over copper wire. Now we use a lot of optical fiber. Usually in a building, when they're outfitting it for computers, we use fiber optic cable there because you can get so many more accurate signals over fiber optic cable than you can over copper wire. we're going to stop here with this video, and we'll pick up with our last video in our next appearance.